Okay, recording starts.
Okay, Vadim, so are we ready then? Okay, so here's and please distribute them to everyone.
Где зачем?
Okay, right. So today I'm going to tell you about Newton's laws, and well, there are three Newton's laws. And have you anyone heard about Newton's laws?
No.
No.
I have.
Okay, so what did you hear?
There are three laws.
Three
The
laws?
apple fell, then
Okay.
he understood everything.
Right.
He was a smart guy.
You're not. Can you name those laws? Yeah, there are three of
The
them.
first one is the one about inertia.
Right.
Then the second one is about force, and the third one is about two forces, that the force and the counter force.
Yes, excellent. So basically, I can summarize that there are three laws. Surprisingly enough, the first one, the second one, and the third one. And the first is about inertia, or you can put it this way: the first law is about bodies or objects that are free, that have no other forces or other objects acting upon them. So basically, the first law tells us what a free object does, or wants to do anyway. The second law basically tells us about how an object moves when a force is acted upon it. And the third law tells us about how one object interacts with the other when, basically one object pushes or pulls onto the other. Okay, and it indeed is enough. These three laws are enough to understand quite much about physics, about how the bodies move, how, let's say, celestial objects move, like Earth, the Moon, and so on. And they are basically in the foundation of classical mechanics. And now you can, if someone asks you where are those laws used, what would be your answer? Almost everywhere, right? Almost everywhere. And now the first law. So the first law can be formulated like that. So an object viewed in inertial reference frame is either at rest, so it's just there, not moving anywhere, or it moves at a constant speed, at a constant velocity, along a straight line, unless there is a force acting on this object. So if you are in an inertial reference frame and you see an object accelerate or decelerate or change its direction, you can definitely tell that there's a force acting on that object. And it just happens to be so that Earth is quite a good inertial reference frame. It's not exactly an inertial reference frame because it rotates around its axis, it rotates around the sun, but up to certain quite tiny errors, you can consider Earth a reference, an inertial reference frame.
And what is an inertial reference frame? What does it mean?
Okay, that's actually a good question. the thing is that well, okay, put simply enough, this is actually a definition of an inertial reference frame. So this basically postulates that such frames exist, and well, the thing is that in nature there are no exactly inertial reference frame. Well, after a very tiny errors, Earth is an inertial reference frame. The Sun is a better inertial reference frame, but it still moves inside of the galaxy and so on. Then the distant stars, as we see them in the sky, are even better approximation to an inertial reference frame. And well, still it appears to be so that they are not exactly an inertial reference frame because they also move. However, the errors which are introduced due to those reference frame that I just named, or the sun, stars, the errors due to them not being exactly inertial reference frame are quite small. So you can consider those as examples of inertial reference frame. And the thing is that, well, if you, let's say, if you are in an inertial reference frame, you're on the Earth, you throw a ball in the air, you see that this ball falls down on the Earth, and that's, well, that's because a force is acting on this ball. Right? So if you could switch off the Earth, this ball would just continue along a straight line. Right. So let me just show you an example of the first law. So basically, the thing is that if there is no force acting on an object and this object is moving, then this object is going to continue to move indefinitely. And here I've got a toy bus, this toy driver, and let me show you what happens if I move it on this notepad. So I'm going to move it. Well, you see, as long as soon as my notepad stops, nothing actually happens with the bus, right? It continues the motion until it's stopped by, well, by these obstacles here. And this is an illustration of the principle of inertia. And can you, I mean, have you encountered the principle of inertia in, well, your everyday life? Can you name an example? Anyone? Like,
when you sit in a car and the car starts to slow down, you continue to move forward.
yeah.
Like this, sitting, but
Yeah.
your body moves forward.
Yeah, yeah.
You feel it.
Excellent, excellent. That's an excellent example. I've got the same example here. So, if the train is in motion, it starts slowing down, and you start falling forwards, right? And that's because you're standing on the floor of that train, car, and when it stops, there is quite enough force on your feet to stop them from moving. However, there is not enough force on your upper body, so you start falling, and actually you need to grab a handle to stop you from falling forward, and that's an illustration of inertia principle. So you basically need a force to stop you from moving. Right. So here there are examples of inertial frames that I've already named, Earth, the Sun, and stars. And now we're coming to Newton's second law. So this is basically a very, so to say, practical law because it basically says it tells you how to calculate force if you know the acceleration of the body, or the other way around, if you know the force acting on the body and its mass, you can calculate its acceleration. And
what is a vector?
Well, you can consider a vector basically just as an arrow which has a direction and a certain length, and there is basically a simple rule which you need to know related to how to add up two vectors. So if this is a vector, let's say F1, a force acting on the body, and then if there is another force acting on the same body, then you can move this vector as long as its orientation stays the same. So you move here, and then from the start of the first vector, you draw an arrow to the point of the second vector, and this is going to be the total force acting on
The sum of vectors.
Yes, the sum of two vectors, which is the total force acting on this body, and this total force is what stands here in second Newton's law. Okay, and you got any questions at this point?
At this point, I think no.
You have other questions?
Yes.
Okay.
Thinking.
Right. So what is it?
Nothing, I'm just thinking.
So you
don't
don't
have any questions. Yeah.
Okay, fine. Right. Now we got a little. Right. Yeah. So these are the units of force. So they are kilograms times meters divided by seconds squared, and they are called newtons, of course, after the unit. And here's a small example on Newton's second law. So if we have this box on the picture, and we know its mass, which is 60 kilos, and we know the force with which we act on this box. And let's say we measure the acceleration of the box. You actually know how to measure. You have an idea?
Acceleration of the box?
Yeah.
No.
Okay.
We use the second law, but I mean how to measure it.
How to measure it, not how to calculate it from this problem.
Oh. We can take the difference of velocities and time, actually.
Right. Right. Or we can take, let's say, we can film it and then on
exactly. If we
so
can measure it without just having a speedometer on it or something, then we need to film it.
Right.
And measure the distance there.
Right. Right. Okay.
Well, I had physics at school, I thought.
Right. So
You remember that you could explain the rules.
let's say we measured, guys. Let's say we measured the acceleration of this box, and the result came out to be 0.5 meters per second squared. And you see that if we had only this force acting on this box, acceleration would be 60 kilos divided, 60 newtons divided by 60 kilos. It would be just 1 meter per second squared. And because of this force that acts on this box and actually stops, well, prevents it from moving too fast, tries to stop it. Because of this force, we have a smaller acceleration, it's just 0.5, and we can calculate from the second Newton's law. So, total force acting on this box is our, let's say, force if we push it, plus the force of friction. Since the problem is one-dimensional, I can just remove the vectors because they are all along one line, and this is equal to mass times the acceleration, and from this I can calculate the force of friction, which is going to be, if I substitute all the numbers, it's going to be 30 units, just exactly half of the force with which we push it. Okay, now let's go on to the third law. Right?
I had a question. Is there a difference between the force of friction and drag? Are there any difference?
Well, sometimes. Okay. Not much actually, because usually force of friction is, I think it's used usually for contact friction when you have two let's say more or less solid bodies, and one of them rubs against the other, and therefore causing friction, and this is called force of friction. But I think it's also sometimes called drag, and let's say the friction against the air when you are moving very fast through the air or through a liquid is usually called drag, not the friction. Yes, but conceptually there's not much difference there. Right. Okay. So now the third law, and it basically tells us that if one object, let's say we have two objects, and if one object acts with a force on another, then the other reacts with a force which is exactly equal in magnitude and exactly opposite in direction to the first force. And here I actually would like to have someone to help me with the demonstration. So, anyone? A volunteer to help me with the demonstration? No? No one?
You can go, Jimmy.
I will not go. You go.
Right.
Come on, it's gonna
You
be
are
fun.
smart.
Well, you don't have to be smart to
Okay,
participate in the demonstration.
Okay, you don't really need to go. Can you just stand up?
Well, okay.
Okay. And can you jump up in the air for me? Okay, excellent. So can you now tell me why didn't you actually remain floating there in the air? Why did you fall down?
Gravitation.
Gravitation. What's gravitation?
I don't know.
Okay, right. So
This is the force that,
Yeah.
well, it's also about Newton, but not
Right,
about
okay.
not about his famous laws. That the law is that two objects are attracted to each
Right,
other,
right.
according
Right.
to their masses. The mass of
Excellent.
Dima is much less than the mass of Earth. So.
Well, you know everything.
Not smart.
Okay, so there's a force acting on you on the Earth. Is there a force acting on the Earth?
There should be.
Okay, why didn't we see the Earth move while we were jumping?
Maybe it moved. We don't know.
Well, okay. My question was, why didn't we see it?
The Earth is big.
Okay, yes, exactly. As You already said the Earth is very heavy,
Mhm.
and its mass